Hi there, welcome to your lesson on basic derivative rules. Let's recap first what we saw in the last lesson, which is a very big idea in calculus and mathematics, the definition of a derivative. We talked about the fact that a derivative is just the slope of a tangent line to a curve. For example, the slope of this line would be the derivative at that point. And we began our discussion with the idea of slope. We know finding a slope on a line is easy. We can use slope formula. Turns out that finding the slope on a curve is the same thing, except for that there are many different possible slopes on a curve. At every x value, at every point, there can be a different slope. For example, that slope, or that slope at that point, or that slope at that point, or that slope at that point. So no matter where you go on the curve, there's going to be a different tangent line which represents the slope at that point. Okay, we figured out the definition of a derivative. We began by finding the slope of a secant line between P and Q, and the slope was this. And then we said, if the derivative is just the slope of a tangent line, we don't want the green slope here, we want the slope only at P. So what we want is this slope, this tangent line. So we took point Q and we moved it closer to point P, because as you move Q closer to P, you get a slope that is close to being this slope, the one we want. We found out, well, how do you move Q? We apply a limit. So we take our slope of the secant, which was this, and we apply a limit to it. The limit says h approaches 0. That means this gap between the point P and point Q, that gap becomes 0. And as that gap becomes 0, it means this point is moving closer, and we're getting closer to getting the slope of this tangent line. So that was our derivative. That's where we ended. We had this thing called a definition of a derivative, and here are two symbols for derivatives. We took that definition of a derivative and we applied it to find the derivative of x squared. So we used the definition and we got to the derivative of x squared being 2x. So f prime x equals 2x, which means the derivative of that. Then we took that definition of a derivative and applied it to x cubed. So the derivative of that function was 3x squared. So we've already gone through that process of using the definition of a derivative. It can get pretty complex depending on the function you're inputting. So now, let's take a look. If that's our definition of a derivative, are we always stuck using that every time we want a derivative function? Maybe, maybe not. Let's take a look. So here's the first one we figured out. This was the function, this was its derivative. The second one we looked at was this function, and its derivative was this. So now look at these carefully. Maybe it doesn't even take a careful look, but you should see some kind of pattern. And if we can spot a pattern in what to do in terms of going from original to derivative, then we don't have to use this definition every time, which can get very complex. So what pattern do you notice, and can you tell me what the derivative of these three would be? Because putting these three in here might be complicated, but look at them and consider this. What do you think the derivative of these three should be? I hope through just a little thinking you're able to come up with this. We can see now what is called the power rule of derivatives. It means when you have an exponent on a variable, to find the derivative you just drop the exponent in front and then you decrease the exponent value by 1. So this was a 2, now it's a 1 here. This one, drop the 3 in front right here and decrease this value by 1. It becomes a 2. So over here, 4 goes in front and this becomes a 3. Over here, 5 goes in front, this becomes a 4. And over here, 28 goes in front, and this reduces to 27. That is called the power rule. It is the most basic rule of derivatives, but we will use it all the time. So if you have a function that looks like this, the derivative is this. Please take a moment to pause and write this down. Okay, try these three here using the power rule. This first one should be simple. Second one, I'll give you a hint. You may remember when you have a denominator with a variable, you can bring it up and it looks like this. So this is the same as this. And then you can use the power rule. Likewise here, when we have a root, you may remember that the power is 1/2. So use the power rule on all three. Okay, first one, check your work there. Second one, notice what happened in the second one. -4 comes to the front, and then a lot of students make the mistake of changing that to a 3, but remember the rule is always subtract 1 from that. Like here we subtracted 1 from it to get 10. When you subtract from a negative number, you get a bigger negative number, so -5. Be careful with that. And C, alright, again, drop the half, subtract 1 from it, You're always subtracting 1, so this becomes negative 1/2, which could be written like this, because we usually don't write negative exponents. So that x then went back to the denominator here, and here it can be the same as that. Take a look at those two in detail so you understand. Okay, so try these two using the same rules. Check your work. First one, pretty basic. Second one, again, using the rule with the negative. Double check your work there as well. Okay, next rule. Next rule is sort of like the power rule, and it begins like this. Now we have a number in front, a constant in front, or a coefficient. What do you think happens? So what would the two derivatives of these two be? What do you think? Let's check what you got. Hopefully you got the same as this. Use the same power rule, drop the 6 down, but now you have a 6 and a 5 in front, so 6 times 5 becomes 30, and this still reduces by 1 from 6 to 5. Second one, drop the 15 down, multiply it by negative 3, and then reduce this by 1. Great, this has a rule, this rule has a name as well, it's called the constant multiple rule. So when you have a constant in front of the function, when you take the derivative, you have the derivative, but you just multiply by a constant. So it'd be the same derivative, but you multiply by the number you have in front. Okay, how about this? What do you think is going to happen here? Now we have these three constant values. There is no variable. So think about what is the power on the variable if there was? If there was an x here, what power would it have? Well, that x would have a power of 0 because x to 0 is like 1. So writing 8 is the same as having 8x to 0. So now apply the power rule. What happens? Okay, so first one is 0, second one 0, third one 0. Okay, so if you have this 0 here, you drop it in front, you have 0 times 8, which is 0, and then you have x to the negative 1 because you reduce it by 1, but you still have 0 in front, so 0 times x to the negative 1 is just 0. So the rule here is whenever you have a constant value, it's called the constant rule, then the derivative is 0 every time. So if there's no variable there, the derivative is 0. Okay, how about this? So we're just taking small steps forward. Now we have x to the 10 plus x to the 7. What do you think the derivative of that will be? I hope you were thinking this. Drop the 10 down using the power rule, reduce this by 1. And then for this one, do the same thing. Drop the 7 down, reduce this by 1. So what will the derivative of this one be? Okay, we have this. 5 drops down times 2. 7 drops down times 9. And then the 10 is a constant. Remember, that becomes 0, so it's gone. This is called the sum or difference rule. So when you have sums or differences of different terms, you just apply the power rule to each term. So the derivative of that is derivative of the first one plus the derivative of the second one. Great. So this is all very good news. And the good news is this. If you have a function something like this, if we went back to the definition of a derivative that we learned last time, we would have this long definition of a derivative, the one based on slope of a secant line, and we would have to put this function into here. Look at what this becomes when we put this function in here. Oh my, alright, so the x plus h had to replace this x, the x plus h had to replace this x, so we can see x plus h twice in there. So there's a whole function with x plus h substituted in. And then we do minus the whole function, so minus the whole function again over h. Now this might look not so bad, but it is crazy, right? If you had to expand these brackets, 5th power, 7th power, you could use binomial expansion, which we've learned, and expand those, but these are going to be huge. This is going to have 6 terms, this is going to have 8 terms, it's going to be huge things, and all this cancellation, it's going to be a giant headache. So the good rule is we have these shortcut rules we just figured out, so you don't have to do this definition of a derivative. You can just use a shortcut. So using the power rule shortcut, it simply becomes this, right? We drop the 5 in front, we drop the 7 in front. It's easy. So much easier than doing this long approach here. This would be crazy if you did this all the way through. Okay, so use the derivative rules we've learned so far to try these. Try A first. And let's check our work. So there's the answer for A. Check your work carefully. It's putting this step in the middle here, which might be a little confusing, but I think you can sort it out. The 12 drops in front, so we multiply by 3 to get negative 36, and then you reduce this by 1, which becomes negative 13. Try B. Okay, B is very straightforward, and it's showing you a different form for derivative. Don't forget, that f primed of x is one way to write it, but dy dx is also another way. So we have 5 turning into 0 because it's a constant, and then here you drop the 2 down and you get 6x. Alright, how about c? In c, take a close look. What are you going to do before you can take the derivative? What do you need to do with this before? Well, I hope you're thinking before, well, I don't know any rule about multiplication like that, so I should combine these. So multiply these through to get this. And then you can take the power rule in each part, which is 2t minus 1 for this one, and then minus 2 becomes a 0. It's gone. Why is this one minus 1? Because the power on this t is 1 right now. Drop the 1 down, you get minus 1, but then you subtract 1 from the exponent and it becomes 0, so the t disappears because it's t to the 0, which is just 1. Remember that anytime you have an exponent like this, sorry, a variable with no exponent visible, which means 1, it just becomes the number you see. Okay, try d. In d again, you might need to do some work before finding the derivative because we don't know how to deal with this division. So take a look at it and you say, okay, well, I see x's everywhere, not here, but maybe the x's will cancel somehow. So how about turning this into 3 separate fractions? One fraction is this over this, the next one is this over this, and the last one is this over this. Once you have the 3 fractions, apply the power rule to each one separately. Okay, let's check how you did. So here's this, written as 3 separate fractions with the same base. This one here you can cancel x4 and x squared to make x squared. Here you can cancel the x cubed and x squared to make x, and here you just have that, but you bring it up to the numerator. Now do a power rule in each part. Drop the 2 for negative 3, and then drop the negative 2, reduce by 1, negative 3. Great. So I hope through these you're starting to get a hang of how to do basic rules of derivatives. This is what this is all about. Try these two. Okay, check your answer for A, and check your answer for B. B has a little bit more going on with the exponents, but we're just practicing all these rules. This is a lot of algebra now, but you got to master these rules in order to move forward with calculus, so keep on trying. How about these two? Try these two out. Notice here it says find the gradient function. When we find the derivative is called the gradient function because the function you create when you get the derivative is the function that will give you the gradient or the slope, right? We talked about that derivative of slope. So there's A. So there's our derivative, and this is called the gradient function because now you can substitute any value for x into this gradient function and find the slope at that location on the curve. How about the second one? Try that one out. Okay, here's the original, simplified a little bit, and then the derivative is taken of it bit by bit, piece by piece. Again, this is your gradient function because you can put any x value in here, and this function will produce the slope of the tangent at that point on the graph. Try this problem. It says find the gradient function of this equation. And then it says, hence find the gradient of the tangent to the function at the point x equals 2. Well, let's begin with the first step. We're going to find the tangent, or the gradient function. So find the derivative of that. There's your derivative. So this is this one simplified, and then finding the derivative, we get this. This is called the gradient function. This function allows you to find the slope at any location on the curve. So as we know, again, this is the gradient function. It allows you to find every possible tangent line. Now, the question says find the gradient when x equals 2. So imagine there's a curve, and by the way, this curve is not this one, but you can see on one curve there's many possible tangent lines. So at every different location of x, there's a different slope, a different tangent. So this is the general equation for any of those, but if we want to find a specific one, like x equals 2, we put the x value into the derivative, and then you get the slope of the tangent at that specific location along the curve. So what is the slope of the tangent when x equals 2? So you put that into your derivative, and you get a value, in this case, of 5. That means precisely at x equals 2, the slope will be 5 of the tangent line at that location. All right, 4 more to finish it off. Try A. Here's the answer. Check your work. Try B. Here's your answer. Check your work. Try C. Here's the answer for C. and then try D. Check your work here. Great job.